Okay, so today I'm going to talk about decimal fractions, which is another kind of another way of writing fractions. We were talking about fractions last time, like 1/2, 7/10, 6/25, 1/3. These are all examples of fractions, but what you're probably also familiar with, especially from using a calculator, are decimal fractions. So 0.5 is the decimal fraction for 1/2. 0.7 would be the decimal fraction for 1/10. This would be 0.24 would be the decimal fraction for 6/25, and we're going to see how to obtain that in a second. And 1/3 is problematic because a decimal fraction in this case is an unending repeating decimal, as you may be familiar with from grade school. So we're going to look into these situations, and we're going to see that there's a way to convert from an ordinary fraction into a decimal fraction, and vice versa. And we're going to learn some ways of writing decimal fractions. So let's take a look at this first one, 1/2. So what we're going to do is take 1 and we're going to divide it by 2. And unfortunately, the way I've been writing division makes us flip that thing upside down. So I'm sorry about that. I have given some thought into how to improve my notation, but I haven't got any really good idea so far. So this is what we got. So it goes in 0 times, and that doesn't seem to help us at all. It says that 1 divided by 2 is 0 with a remainder of 1, which is pretty much where we started. But we can write 1 as 1.0. And now I have, how many times does 2 go into 10? It goes in 5 times. And gives me a remainder of 0. So my division is done. Now I probably should write this a little more carefully. Line up my columns here, and I have a decimal. Just like I introduced the decimal here, I have to introduce a corresponding decimal here. So it gives 0.5 as my quotient. And that's nice because I can get a remainder of 0 when I do a division that way. And you go ahead and try 7/10 a similar way. It's going to be very easy to do that one. Let's try 6/25 over here. So I've got 6 and I divide by 25. Goes in 0 times. Now I'm going to put in my decimal. How many times does 25 go into 60? Well, it goes in twice. And now I'm going to add another 0 here. How many times does 25 go into 100? It goes in 4 times. And since I put a decimal point here with 2 digits following, I've got to put it there. I'm going to have 0.24. For 100, 0. Again, remainder of 0. So perfect division, 0.24. So many divisions I can do this way. But not all of them. We do get into a problem. So suppose I take, I want to figure out what 1 divided by 3 is. So 3 goes into 1 0 times. And now I'm going to add my decimal. How many times does 3 go into 10? It goes in 3 times. And that gives 9, 1, 10. So you see, I've repeated, this 10 has repeated twice now. And actually the 10 was a 1, and then I brought down a 0. So this 1 was what was repeated. I had a 1 as a consequence of this operation here, and I got a 1 here. And guess what? I'm going to get another 1 here. So I keep getting 1, 1, 1. I'm going to have 1s all the way down. So the results here are going to be the same over and over again. This process doesn't come to an end, which is a bad thing normally in mathematics. But Here, I mean, we just have to cope with it. So what we do is write 0.333 and so on. That ellipsis, that dot, dot, dot is an ellipsis, and it tells us to keep going with the same pattern. So I'm just repeating the 3 over and over. And some people don't like that ellipsis. It's not quite precise enough, so what they'll do instead is write a bar over the 3, and that means I just keep repeating the 3 over and over again. So that is another example of a decimal fraction, and those are the only kinds of examples we have. We have these so-called terminating decimals, like 0.24, 0.5, 0.7, they terminate, or we have an infinite repeating decimal, and this one is a 0.3 is repeating. We can have a longer repeating chunk, but I'm going to claim that that when I do convert a fraction, any ordinary fraction, into a decimal, I am going any rational number, I mean, into a decimal, I am going to get a repeating decimal. Why is that? Well, it's always the same idea as this case. So this 1 here is a partial remainder, and as such, it has to be a residue mod 3. So there are only 3 choices for residues mod 3. There's a 0, a 1, or a 2. And that means my whatever number appears here, 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 and so on all the way down has to be from this finite collection of choices. They have to be residues mod 3. There's only so many that we can choose from, so we eventually have to end up repeating ourselves. Right here, in this case, we repeated ourselves very early on, but no matter what, we're going to have to end up repeating ourselves eventually. Terminating decimal will just repeat 0 over and over, but a non-terminating decimal will repeat these non-zero residues. And it may repeat them in various patterns, but once we've got a result, and even if it cycles some kind of pattern here, it'll have to cycle back to this result, and it'll cycle through the same list again. So let's take another example. This one's going to be kind of complicated. It's going to be long and messy, but 1/7 is a bad one, but it's going to illustrate my point. So I'm going to divide 1 by 7. So I'm going to make lots of room for this. Here's 7, 1. Okay, so that was very badly drawn. I'm going to fix all that. Sorry. Okay, let's put it right in the middle here. Okay, so I want to know how many times 7 goes into 1. Well, that would be 0 times. So there's my residue 1. Now I'm going to bring down a 0. Makes a 10. How many times does 7 go into 10? It goes in 1 time. I should draw that a little further down here. 1 time. Pencil. 7. Now there's my residue is a 3. So I had a 1 and a 3. Okay, next. I bring down another 0. How many times does 7 go into 30? It goes in 4 times. Residue is 2. So I had a residue of 1, I had a residue of 3, and I've got a residue of 2. I'm going to bring down another 0. How many times does 7 go into 20? It goes in twice. 14. I got a residue of 6. Nothing's repeated so far. I've got a 1, a 3, a 2, and a 6. Bring down another 0. How many times does 7 go into 60? That would be 8 times. 56. 4. I got a 4 now. So I had a 1, a 3, a 2, a 6, a 4. Starting to get a bit tedious, eh? 5, 35, 5. Now I got a 5. It's a different one. Bring down another 0. How many times does 7 go into 50? It goes in 7 times. That's 49. And there's a 1. So you see I've now repeated my 1 as a residue. So if I bring down a 0, I'm going to get 10, and this whole chunk will repeat over and over and over again. So even though in this case the decimal is very long, it will repeat. So this is the repeating chunk. And if you want to write it with an ellipsis, it's going to look like this. You should see the pattern at that point. So that is a longer example of a repeating decimal, but you see the residues mod 7 are 0, 1, 2, 3, 4, 5, and 6. And here are residues 1, 3, 2, 6, 4, 5. And there's no more choices. I mean, a 0 would be a choice, but that would lead to a terminating decimal. I've used up all my possibilities, so I have to end up cycling back to something I've seen before, and I do indeed. I cycle back to 1. I don't have to cycle all the way back to the beginning. Sometimes you end up cycling only part way back, but you do end up cycling, and then things just repeat themselves after that. So that should convince you that we always get a repeating decimal fraction when we divide a rational number and express it as a decimal fraction. Some cases we do get a non-repeating chunk before we get a repeating chunk. So here is an example of a repeating 3/8 after a non-repeating initial chunk here. Okay, so that can happen too. You may ask, oh, you may say, I don't believe you. What is the fraction that leads to this? Well, that's what we're going to investigate right now. We're going to try to see how to convert this thing into back into a fraction. So we're going to do the reverse conversion. So let's do it. Let's turn to this. Here's one way of doing it. I like this method. So I'm going to write down my number, and I'm going to call it n. It's some unknown number, so I'm just going to give it a mysterious letter of the alphabet, n. And I'm going to do a couple of things to n. I'm going to multiply it by 10. Then I'm going to multiply it by 100, and then I'm going to multiply it by 1,000. I'm going to see what we get when we do that. Multiplying by 10 shifts the decimal point. So that's actually pretty easy to see what the answer is. I don't have to do any kind of calculation. I just have to physically move the decimal point. When I multiply by 100, it moves the decimal point again. Now when I multiply by 1,000, it moves the decimal point one more time. Okay, so eventually, after moving the decimal point enough times, we're going to see two of these products here are going to have the same tail. 3, 8, 3, 8, 3, 8. 3, 8, 3, 8, 3, 8. Right. So that is going to give us a trick. Now we normally have difficulty dealing with infinite things. They just keep going. We have to keep working, and we never finish working. But in this case, I can actually stop. So 1,000n. Let me write down the second one that I got. And 10n. And in this case, something very nice happens. If I subtract them, what's 1,000 minus 10? That's 990. So 1,000 n's minus 10 n's is 990 n's. And I could write down 990 n's, but that would be very tiring and boring, so I'm not going to do that. Now 238 minus 2 is 236. And when I subtract 3 from 3, I get 0. 8 from 8, I get 0, 0. So there's this beautiful zero, set of zeros. That's why I specifically chose these two products here, because they have the same decimal. So when you subtract them, you just get a whole tail of zeros. And so now this gives us a way of finding n. We divide our fraction, 236 divided by 990 should give us the fraction. So let's test that and see what our calculator says. And I'm afraid I'm going to blow your mind once more with my reverse Polish notation calculator. You should get one, but nobody will. Okay, I'm not showing enough decimals. I'm going to have to show me some more decimals. There. 0.2383838, which is what we started with, and that led to the fraction 236 over 990. Which is correct. When we plug this back into the calculator to test it, it gave us the thing that we started with. So yeah, we found it. We've been able to convert this decimal with a non-repeating initial chunk and then a repeating chunk into a fraction. We can always do this kind of operation. So you just have to be a little bit clever about it. So you have to keep multiplying by 10 until you see the same tail twice, and then you subtract the two things. You're going to get a whole bunch of zeros, which means you have two integers here, and when you divide the two integers, you get a rational number. So every decimal with an eventually repeating tail converts into a fraction, and vice versa. Okay, one more thing we have to do with this. If you have been observant about our fractions, let me write down this answer again, 236 over 990. This is not in lowest terms. So really, to give a complete answer, we have to put this into lowest terms, or sometimes called least terms. How do we do that? Well, we find the GCD of 236 and 990. 236, let's see, can I do a factor tree? I don't know if I can do a factor tree, so let me do, let me just pull out my calculator. So 990. I'm going to take 236 from it. So I got 46 here. Okay, now let's keep subtracting 46 from 236. Six. Let's keep subtracting 6 from 46. It's easier to, it's more efficient to do division, but I'm just in the mood to do subtraction Euclidean algorithm. Okay. Finally, that I can do without the aid of a calculator. And so, one 118 over 495. Let's double check that one more time. 118 divided by 495. 0.238, 3838, and so on. So that preserves the necessary property of our of our quotient. In other words, that it equals the decimal that we started with. All right, so that's kind of nice, and that often appears on exams. Hint, hint. That question about being able to find a rational number given a repeating decimal. And you not only have to use our trick to find a rational number, but you should also put it into least terms by a familiar process, or lowest terms by a familiar process of taking the GCD. Okay, so that is the technical part of this. That's a kind of an interesting connection to make. Now, there's one last thing I'd like to say about this infinite decimal business. So let's take this very interesting infinite decimal, 0.99999. That is our number n. I want to see what fraction it is. So I'm going to multiply them by 10, and I'm going to get 9.9999, and my original n was 0.9. So already I've got, these two have the same tail. Everything after the decimal point is what I'm calling the tail, so they're the same in this case. So I can just subtract these two. And I'm going to get 9n's is equal to 9.000, so 9. What is my fraction? N is equal to 9 over 9, and I put this into least terms. GCD of 9 and 9 is 9. It's 1 over 1, also known as 1. So this gives us something that may appear very bothersome to you at first, but I'm afraid it's true. 1 is equal to 0.9999, and so on. So these are equivalent ways of writing the number 1. That is an unfortunate aspect of our system of decimal fractions. Some numbers have two different representations. It's just a fact of life. It's something that isn't taught in schools, and so most people who haven't taken university level mathematics don't know this, but believe me, it is 100% true, 100% accurate. And it is a little bit unfortunate. It does lead to some difficulties when we do mathematics, very precise mathematics, talking about the number line and the geometry of the number line. We end up running into problems because of this dual representation issue. But those problems have all been overcome, and the system is consistent as far as anyone knows. Anyway, I think I'll close this with my favorite math joke of all time. I know I haven't been giving you enough math jokes in this course, so here I'm going to try to make up for that. And the question is, how many mathematicians does it take to screw in a light bulb? And you may want to pause. I will give the answer. So pause, think about it, and here's the answer. .99999 repeated. All right, thanks. I'll be back with more math later. Bye.